Hello everybody and welcome back to this new video, and today we are going to be talking about something a little different. We are going to be doing a talk about ELF binaries, and we're going to take a deep dive into ELF binaries to see what they really are and what they could mean to us in our lives. So without further ado, let's get started. So first off, a little overview. We're going to be doing a short introduction. We're then going to be talking about what an ELF file actually is, why we should know about them, why they're interesting to us, and what we can learn from them. We're gonna take a tour and see how does source code become a binary, what happens with that. We're then going to take a deep dive into the actual structure of an ELF binary, and we'll see what happens when a binary gets executed, what are the steps that the operating system is going to take, and lastly, a short detour to talk about static versus dynamic binaries. Alright, so let's get started with this introduction. So I am Pink Draconian. I have a YouTube channel. I have a Twitter account, so follow me, subscribe. I make videos usually solving challenges and boxes from Hack the Box, from CyberSec Labs, from all different kinds of websites, and showing how they work. And I usually try to incorporate a education thing into it, so it's not just showing what the solution is, but also showing how do you get to the solution, what does every step mean, and how does that work. So if you're interested in that, go check that out. I'm also very into penetration testing, so I have professional experience as a penetration tester and software developer. I am really into cybersecurity, and this year I am finishing my degree in AI. So that's who I am, but let's get into the ELF binaries. So first of all, what is an ELF file? So over 20 years ago, before I was even alive, in 1999, ELF was chosen to be the standard file format for binaries for Unix and Unix-like systems. So ELF stands for executable and linkable format. And it kind of defines a structure for binaries, but also libraries and core files. So when I talk about an ELF binary, that's not always the same as an ELF file, but this talk is mainly going to focus on the binary part, so I kind of interchange them. But so it defines a structure saying, okay, every binary is going to look like this. So this specification kind of allows the operating system to interpret these files and to interpret the underlying machine instructions, because a binary contains machine instructions that the operating system needs to interpret, needs to execute, so they need to know how that works. And an ELF binary kind of says this is a specification as to how they should be formatted and how they should be used. So ELF binaries are the output of a compiler, and usually when you talk about kinds of files, you can say, okay, this extension fits with that file. However, for ELF binaries, you can see there's a long list of ones that could apply, and even none can apply. So yeah, that's pretty much like a little overview about ELF binaries and what they are. And now we can go in deeper and analyze them. But first of all, I want to tell you about why you should be interested in this. Why should you know that? And pretty much everybody should know this. Why? Well, first of all, general knowledge. You are using a computer, you are doing something with security, something with computers, so it's always good to know at a low level how something works. Because if you know at a low level how something works, then you can abstract that to higher levels and you can apply that to different kinds of things, because in the end everything kind of comes down to the same thing. So it's important to know about as many things as possible, so I think just for general knowledge it's good to know this. However, also if you're a developer, it's very good to know this. Why? Well, if you write code, your computer is going to execute your code, but there's a lot of steps between them. And if you can kind of know what happens in between them and what actually happens with the code that you write, you obviously get a better understanding of what you're writing, making you a better programmer. Then we also have the standpoint of a blue teamer, incident response. And this is pretty much, well, you're working for a company or you're working for something, and you have to protect that. And attackers are going to use binaries to attack. Attackers are going to exploit binaries you have. And what if an attack happens and you need to see what happened, what went wrong, how did they get in? Well, then knowing about these files and about what these files do is obviously very important. Then the same goes for digital forensics and malware researcher. It's very obvious why they would need this. And then also red teamers and penetration testers, because we are obviously going to use these binaries to breach, to exploit them, but we're also going to create them to do something. So we're going to create binaries, but we're also going to exploit existing binaries. And in this video, I'm going to mainly focus on the red teaming and the penetration testing part of it, because that's what I'm most interested in. But first of all, some more general knowledge. We're going to see what happens to source code to become a binary. So for this, let's take C as an example. So we have source code written in C. And what do? Well, we use GCC, obviously, to get a binary. And what's GCC going to do? Well, it's going to first compile our source code into assembly code. That assembly code is something that we can see, for example, in Radare or in Ghidra. And it's something that we can still kind of understand. But then an assembler is going to take that assembly code and it's going to convert that into object code. And object code is kind of the lowest level, and it's what your computer understands. And then lastly, you can have a linker that's pretty much going to link your object code to the reference libraries. So all the libraries it uses, it's going to link all of that together so it knows where everything is found, stuff like that. And that's how you end up with a binary. So it's kind of important to notice so you're aware of what is happening. And then this is also interesting because when you are going to be decompiling or disassembling a binary, for example, Ghidra can decompile, which is going to disassembly is going to go from object code to the binary itself to assembly code. Assembly code is still hard to read, but then if you've used Ghidra before for reverse engineering, you will know that that is able to kind of generate back pseudo C code again. So that's going to be decompiling then. So it's going to be going from assembly code back into source code. So these are some terms that are quite important in the reverse engineering and binary exploitation fields. So moving along, the biggest part of this is going to be the structure of an ELF file. And the main structure is we have a header and we have some file data. And file data can be very extensible because the ELF file format is very extensible. It can be used for various different kinds of things. But we're going to focus on binaries, and for binaries we then have program headers or segments, section headers or sections, and then the actual data of the binary. And we're going to go into these a little bit deeper now. So first of all, the ELF header. So we can view the ELF header with readelf-h, and then it's going to show us what that header looks like. Now the first thing that we'll see is some magic bytes, and the magic bytes at the bottom here as well. You can see that we have 7F and then the letters ELF. So those are the magic bytes used by the operating system to verify that this is an ELF file. We then have the class, and the class is going to define whether it's 32 or 64-bit. So in this case it's 64-bit, and we can see that byte is 02, so that is 64-bit. Then we have the data field here, and the data field is very interesting also for binary exploitation, because this is going to define whether it's the binary is using little or big endianness. So whether it's little or big endian, if you don't know what that means, maybe you've heard of least significant bit and most significant bit. So the endianness is pretty much going to describe how your data is actually being stored. And I have this little graph here that's going to better show that. So for example, if we use little endian, then that means that the least significant bit is going to be stored first. So in this data, 01, 02, 03, 04, the least significant bit here is 04. So we're going to put 04 in the first address, then we're going to put 03. So from the least significant bit up to the most significant bit. And then big endian is the opposite of that. And this can be a little bit confusing at first because you would think like, why is this the case? Why would this be a thing? And to be fair, this is a thing that was first used a long time ago. Why? Because it was more performant for some systems to use little endian, for some to use big endian. So different creators of different manufacturers use different kind of stuff, and in the end, well, when you want to bring all of that together in one format, you need to be able to support everything. So that's why this is the case. But this is very important for binary exploitation, because as you could imagine, if you get back, for example, a leaked stack address, you need to know, well, is my binary little endian or big endian? Because if you for example, think your binary is little endian, but it's actually big endian, the address you're going to get back, you're going to process that wrongly, and it's not going to make sense, and your exploit is not going to work. And that's why, for example, in pawn tools, when we unpack some data, we supply whether it's little or big endian, so it knows how it's actually how it has to handle them. And the difference between endianness is very simple in that if you look at the source code for pawn tools, you'll see that this is the code that deals with endianness. So if endianness is little, it's literally going to reverse the data, where data is bytes, is an array of bytes. So it's literally going to just reverse that. So it's incredibly simple, but very important because it can make a script not work, and you might not know why. Well, it might be because of endianness. So now you know where to find endianness in your binary. Next up, we move along to version, and there's only one version of ELF at the moment, with no real plans to get another one, so this is always going to be one. Moving on, we also have the operating system slash ABI, so OS is operating system, and then ABI stands for Application Binary Interface. Now, if you hear that and you think, what is that? But you may have heard of API, which is Application Programming Interface. Well, it's kind of the same as that. However, an ABI works at a lower level. So an ABI is a way for your operating system and the application to know what to expect from each other, to interface between each other. So to better understand this, we can obviously think about an API, which is also going to interface between software at a higher level. However, as a programmer, as a red teamer, as a penetration tester, this is not something that you're usually concerned with, because this is something that's really only the compiler, the operating system. Those are really the only. If you're writing compilers or operating systems, you're going to have to deal with that, but usually you're not going to get into contact with that unless you try to compile in different programming languages or for multiple compilers, stuff like that. However, that's incredibly rare. So usually that's really not something to be concerned about. Then moving on, we also have the type of the file. This can either be a core file, a shared object file, which is dynamic, and that's for libraries. Then we have exec for executable files, and rel for relocatable files. And then moving on, we also see the entry point address, also very interesting because that is where the actual, where your program is going to jump to after it's done all of its preparation stuff. So that's where your actual program, your code, is actually going to be executed. That is the entry point of your binary. And this is also obviously interesting when doing reverse engineering to know the entry point, to know where it's going to start. And then the rest of this is all information concerning the other program and section headers, which we are going to jump into now. So okay, next up we have the program headers or segments. And the program headers show what kind of segments are used at runtime, and it kind of tell the system how to process this file and what to do with it. And for example, we see this interp here. This is going to tell, say, the location of the interpreter that is to be used with this and a path name to it. We have this load here, and this load is going to specify a segment from the file, from the ELF file, that needs to be loaded into a virtual address. So what's going to be happening is this is going to define the length that needs to be allocated. So it's going to allocate that length of space and then move a certain part from the file into that space. So it's going to specify what needs to be loaded into memory. So that's also very interesting to know about, what parts are being loaded into memory. Moving on then, I'm not going to go into everything, but then we have the GNU exception handler frame. This is also interesting because this is going to specify a sorted queue used for storing exception handlers. So when your program breaks down, when you have an exception, this is where these handlers are being stored and used. So I found that interesting. And then lastly here, I'm going to talk about the GNU stack. So this is going to pretty much define the stack, so where the stack is going to be stored, stuff like that. Basic stack information, and if you don't know what the stack is, at a very high level, it's a last in, last out kind of data structure used for storing variables, storing everything your binary needs to use, everything that changes during runtime. So imagine a stack as at a restaurant, a stack of plates that's going to, so if you take a plate from a stack of plates, you're going to take the top plate. If you put one back, you're going to put it back on top. So that's kind of how a stack works. So it grows and shrinks. However, in this case, we have to turn it around upside down because that's how it works here. And that's a stack. But there's something even more interesting here for us as pentesters or as binary exploitation people. And that is the fact that we see a small difference here. So right here, we see that it says read, write, execute. And on the other side here, if this pop-up would go away, yeah, we see that it only says read, write. So what's the difference here? Why is the stack on the right executable and the stack on the left not executable? And why is it important? Well, if you think about the kind of protections that you can have on a binary when you're doing binary exploitation, you might come up with the answer here yourself. And it has to do with the NX bit, the no execute protection. What is that going to mean? Well, if a binary has no execute enabled, that means that of all your memory, memory can either be readable, writable, or executable. So for example, the stack, in this case, the stack always has to be writable, because that's where you're going to be storing variables and reading variables from. If NX is enabled, then you cannot execute anything on the stack. Your program itself, the actual code, is obviously going to be executable, because that's what you're executing. Why is it important? Well, if we have a buffer overflow, and we can write what we want onto the stack, and we can overflow return addresses on the stack. If this NX bit is not enabled, we could put some shellcode on the stack, and then jump to that shellcode and execute it, because we can write there and execute there. However, if we enable NX, then we can write that shellcode still, but we will not be able to jump to that, because the stack is not executable. And that's what we see here. The binary on the left here has NX enabled, so the stack is not executable. And on the right, that's not the case. So that's very important to know about. Definitely when you're doing binary exploitation, you will have come into play with this. So it's very interesting to know how this actually works at a program header level. And then we're going to be moving on to the section headers of the sections. So these are pretty much going to define sections used for like linking and relocating. So I'm going to talk about a couple here. So we see .text. Where do we see it? There, .text. And .text contains the executable code. So the actual code that is being executed. We then also have .data. .data right here. .data contains initialized data with read and write access. And we have .row data, which is read-only data, so that's data that you can't write to. And then .bss is uninitialized data. And then lastly, one more important thing, or one more interesting thing here that you as a doing binary exploitation may have come across is the GOT, the global offset table. This is a table in a binary that's pretty much going to contain an offset for every variable. So if you need to know the location of a variable, you can go to the global offset table, and it's going to tell you the offset of that variable inside the binary. So for example, if you need to find where put is, a put function. So I said it wrong when I said variables. It's mainly symbols, so functions and stuff like that. If you need offsets to those, you can find them there. You will have come across this while doing binary exploitation. When you wanted to, for example, leak a libc address, stuff like that, you will have probably come across this. So that's something that's also just a segment that you can find in your segment header. And that's pretty much all for the structure. So past that, we also have the data of our actual binary, of course, but that's something that lies outside of the ELF structure. So that's the whole structure, and I think for the structure, what you should take away from it is that a binary, an ELF binary, is just a file, and it's built by actual people, and it's pretty easy to understand. And we'll go into that a little more here, because let's say we wanted to write our own operating system. What would we need to do to be able to execute an ELF binary? Well, let's see. First of all, we obviously need to check the magic number. Is it actually an ELF binary? Then we are going to read the header to get all of that information, to know information about little and about endianness, all that kind of stuff. Next up is the program header, and from the program header, we are going to be determining what segments need to be loaded. And we need to load the load segments, and for them we need to allocate space, so allocate some virtual memory space, and then copy that segment from our file into that allocated space, because that's data that is needed. And then lastly, all that's left to do is to actually jump to the entry point that we can find in the header that we saw earlier. And that's pretty much, in very crude lines, what needs to happen in order to execute an ELF binary. So you can see it's not that difficult. It's a very extensible file format. So the specification is over 100 pages. It's really long. But when you look at it and when you kind of abstract it a little bit, you can see that it's not that difficult to understand. And what I learned from making this and from researching this is that I actually came across a lot of things that I already knew, but I could put in a kind of new light. I could understand more deeply, and from understanding it more deeply, I'm not going to remember that in the next 6 months, but that concept, that higher level concept, is still going to be better understood by me because I researched that deeper. And that's why I also think it's very important to go and do this. Research something that you think you might never use and see what you can learn from that. And maybe you might not learn nothing, but you might learn a lot. And is that a risk you're willing to take? Well, I think so. And lastly, to finish this all off, I wanted to talk about static versus dynamic binaries, because as a penetration tester, this is something that you will come across most likely. So binaries can either be statically or dynamically compiled. What does it mean? It all has to do with kind of the libraries that they contain. Why? Well, dynamic libraries, they require external components at the operating system. So they need to use things that are already present on the machine. So if you move a dynamic binary from one machine to another, it's going to use a different resource, and it's going to have to find that different resource on that machine. That is not the case for static binaries, because static binaries, they self-contain everything. So everything they need, they have in them, which means that the files are going to be way bigger, because they have to have all of these external libraries, reference libraries in them. But they're also going to be way more portable, meaning that you won't get into a DLL or a dependency hell when moving them between machines. And this is interesting for penetration testers, because as a penetration tester, you're going to want to compile maybe an exploit, something locally, and run that on your victim. But your victim might not have the newest libraries available, or might not have something available that you need in your exploit. Well, if you statically compile them, that's not going to be an issue. So this is something to take note. If your binary doesn't work, check, is it statically compiled or dynamically compiled, and what happens if I try statically compiling it, and see if that makes a difference. And then the difference can be viewed with the LDD command on Linux. So just thought I'd add that. And that's pretty much it for this talk. I hope you enjoyed it. I hope you learned something, or at least gained some new way of looking at these binaries that you're running every day. And I want to end off with this slide again, and say that this is not usually the type of videos that I make. Usually I make walkthroughs through challenges. So if you're interested in that, check it out. I try to always go into depth for some of them, and I'm also going to, in my Introduction to Binary Exploitation series, so where I explain binary exploitation by doing actual challenges, starting from very easy, going more difficult. I will be referencing this and some of the stuff I talked about here in those videos as well, because for people that want to take that deeper dive. So yeah, follow me on Twitter, subscribe on YouTube, send me a DM if you want to talk to me, and yeah, I hope you enjoyed this video, this talk, and I hope to see you back for another talk in the future. So take care, goodbye.